Good morning, everybody. It's a real pleasure to introduce Noeline Prins, who's a postdoc in biomedical engineering. She works with Abhishek Prasad, worked with Justin Sanchez during her PhD, and has been really instrumental in working on this project. Amazingly, Noe seems to balance all the efforts of doing this research with full-time research in the lab with monkeys doing neural recordings, and juggles all of that to mentor students and actually get these projects done. So it's a real privilege to introduce Noeline Prins, who will talk a little bit about brain-machine interfaces.
Thank you, Ian. Okay, so I'm going to be presenting one of the clinical trials we completed a few months ago, mainly focusing on the restoring upper extremity functions. So moving to paralysis, I mean, all of you, you're not new to this, but about 5.3 million people currently suffer from paralysis. About 60% of these cases are due to stroke and spinal cord injury. And there are more than 17,000 new cases of SCI each year. The majority of these cases are due to falls and motor vehicle accidents, contributing to more than half. And again, 47% of them are actually due to, they result in incomplete tetraplegia. About 15 years ago, Kim Anderson published this paper where she sent out a survey to about 700 SCI subjects, asking them to rank which function would they like to see dramatically improved. And she came back with the results showing that among quadriplegics, they would definitely like to have their arm and hand function restored, far above any of the other categories. So hence why we were focusing on that. So at the MAMI project, we would like to see people who are paralyzed to walk again. But it doesn't start just from being in a wheelchair to walking again. There are several intermediate steps that need to be followed. And we want to present brain-machine interfaces as one of those in conjunction with whatever therapies that are already happening. We're now presenting this as the all and in all solution. So what is brain-machine interfaces? Put in very brief, brain-machine interfaces basically interprets your thoughts into some executable action. We can collect signals from all the way inside the brain. It could be spikes or local field potentials. It could be from the surface of the brain with ECOG arrays, or from the surface of the scalp with EEG. Typically, to collect spikes, you have an array, typically about 96 channels, that's in size smaller than a penny. And this is fed into the second component of the brain-machine interface, which is pretty much the hub of the BMI, basically where we extract the features. These features are basically what the computer will understand as the characteristics of these brain signals that we're trying to interpret. So we do some manipulations to that, feed it into a decoder, which is pretty much the algorithm that interprets these signals. And these can be translated into an executable command, which can be fed into either a computer cursor, an FES device, a robot, pretty much any device. You're limited by your imagination to connect any external device to this output. And typically, the loop is closed by giving a feedback, which is what we call closed loop in brain-machine interfaces. This can be just as simple as a person seeing the result of the output, or sometimes it's even given back to the person in terms of like a stim, or in terms of back into the brain. There is research that's also working in that. So what are the brain-machine interfaces out there? I don't want to take too long to explain those, but I want to show a study that started about 15 years ago, the BrainGate trials. If you notice, all of these subjects have a pedestal that's sticking out of their brain, which is basically where they collect the data, and then they feed it either into the computer, where a person can type emails, can play video games, can communicate with others, or they can feed themselves through a robotic hand. So here at University of Miami, at the Miami project, we wanted to do something a little different, and which I will talk about in a second. So our brain-machine interface trial, we were focusing solely on having the system completely internalized. So we do not have, so if you see our subject walking around, he does not have anything sticking out of his head. As a precursor to all of this, we did a clinical trial, we did a preclinical trial with EEG, where we studied several subjects. These 5 SCI subjects completed the study up to 16 sessions, and we compared them with 5 control subjects. And what we found out is that motor imagery, we found out that yes, the SCI control subjects are able to regulate their motor imagery in order to drive a brain-machine interface. And this was the system we had. This was the system we had. We had a EEG system where we recorded from 20 channels, out of which 5 we used for the brain-machine interface. And typically, this was the experiment setup. We had the subject connected with the EEG system, which was completely wireless, and the instructions were displayed on the screen. And if the decoder interpreted it correctly, it would be fed back into the arm for the person to open and close their hands. And what we found out, so this is a typical experiment, the timeline. So we had them relax and then think about moving their dominant hand to create motor imagery. And these 2 states were the 2 that the decoder tried to interpret. And if it was interpreted correctly, they would get a stimulation, which typically lasted about 10 seconds. And if the decoder interpreted it wrong, they would not get any stim. What we found out when we analyzed the motor imagery data is that the ERDs among the SCI subjects during motor imagery was lower than the rest period, which is expected. In the control subjects, it wasn't as prominent. This is not unusual because, try to think about this. When you're moving your hand, you're moving it, you're not thinking about moving, you're not conscious about it. But if you're asked to create a motor command but not actually move, for a person who can move their hand, it turns out it's actually difficult, and it shows up in the data that the difference is not so prominent. But in the SCI subjects, moving their hand and the thought to move their hand was pretty much the same, so we saw a big difference. So this is what the decoder tried to manipulate, and we got about 70-75% accuracy in trying to differentiate between these signals. So I'm going to show you a small clip. There's instructions are displayed to relax and then to think about moving. And then the FES would open and close the person's hand. I think it's repeating. So this was very exciting for us to some of our SCI subjects who have been paralyzed for years would come and see their hands open for the first time. It was really exciting to watch. So then, once we were done with the preclinical studies, we moved on to the clinical trial. And our system basically was, again, completely internalized ECOG system, which wirelessly communicated to the computer, which in turn wirelessly communicated to the orthosis. We had actually I see several people already here who are involved in the project, but Dr. Jagged and Dr. Prasad were our PIs. Moving on to the system. So as I introduced before, the brain-machine interface has 3 components. The first one being where we collect the data. Again, all of you are familiar with the DBS pacemakers, the Activa PC. With Medtronic, released an investigational device with their IDE, where instead of just stimulating the brain, you could also record the brain signal. So this is the device that we use. So we wanted to take a device that was completely available and repurpose it for a BMI. So that was our first component. And the second component was just a regular laptop with computational power enough to run all the algorithms. And finally, the third component was the orthosis, which is Bioness, again used for rehab purposes. Then we had our subject come in. His injury was C5, and he was Asia A, motor complete. You see the injury? I don't know if it's clear here, but next thing we did was we did an fMRI where we asked him to do some shoulder shrugs, asked him to think about moving his hand, and we tried to narrow in on where that area of the brain was in order to identify the hand and arm knob in the motor cortex. And this is where we plan to put the arrays. So these are the 2 electrode strips that we put in. Dr. Jagged, Dr. Ivan, and Dr. Kahigas did the surgery. And so these are the 2. In the Activa PC system, you have the stimulation leads, which was completely disabled in our system, and we used only the sensing component of it just to minimize the risk. Again, we did this for the first time, and we wanted to make sure that there was no adverse side effects, and happy to report that we did not see any. After 2 days, the patient went home, and then after 2 weeks, he came back to the lab. And the first 2 weeks, what we did was we tried to find technology is not agreeing with me. I hope that's clear enough. We tried to find which of these electrode combinations would give us the best chance of decoding rest versus move. Thank you. And so for 2 weeks, he came 3 times a week, and we would collect some data and try to interpret, run it through our algorithms, and make sure that we're able to decode rest from move. This is what our system looked like. The instructions were displayed. The transmitter was placed under the clavicle, and it communicated wirelessly to the receiver that was basically in a pocket outside the shirt. And again, the computer wirelessly communicated with the orthosis. So this is what the results look like. We had 2 raw channels and 2 power channels. In the raw channels, the spectrograms showed a significant difference between the rest and the move, as we would expect. And so I want to show you some of the experiments. This was very early on. Instructions were displayed, and he would think about moving his hand. It would be interpreted, fed back to the orthosis, and it would open and close. So he would come to the lab 3 times a week, do this about 100 times. 100 times where the hand would open and close. A little bit of mathematical jargon. This is the rest phase and the move phase, the raw signals, which was converted to the power. And we would average the power in different frequency bands. And that was what the decoder would identify as features in order to interpret the difference of these two. And the results show, so this is from week 9 of the study. We started around 55% accuracy, but within the first week, he jumped to above 90% accuracy. And through the 10 weeks that we conducted the study, the accuracy remained about 89%. One of the things that we want to make sure is that this is reproducible and that this is not a fluke. And so a lot of work happens offline where we interrogate the system and the signals to make sure that this is robust. So it turns out, yes, it is robust. So this is the accuracy we saw during the experiment online. And using the same decoder, we saw very similar accuracies offline. And we tested a bunch of other algorithms to make sure that we have tested the best before and after. And turns out, yes, of the things that we tested, the one we chose and implemented gave the best. So after a couple of weeks, again, think about this. You're doing this 100 times. Our subject is getting very bored. And we also want him to have some meaningful action with this, not just for the wow aspect of it. So we had him try to move things in the same brain-controlled phase with the same time limitations. We asked him to move things. So this video is the very first day that he tried that. So if you notice, it's very jittery. He is able to pick it up, but it's not as smooth as one of us would do it. And so after a while, actually not even after a while, the same day he was like, give me a challenge, I can do this. So he wanted us to test him, how many times he was actually able to move this accurately. So we put some concentric circles, and we had him move a cup from one place to another place, and basically scored him on how many times he can get the bullseye. After a week, he was like, I think I need more of a challenge. So we gave him, actually it was his idea, to give a piece of checkers, and he would pick it up to test more fine motor skills. And he improved in accuracy in how well he's able to place the object from one place to another place. The blue is for the cup, and red is for the checkers. We also had him do the Jebsen-Taylor hand function, a modified version of the Jebsen-Taylor hand function test, and he improved significantly from week 1 to week 30 when the study ended. This is a sample of his handwriting. Week 9, he was not able to complete any of the tasks, even with the orthosis, but by week 29, you see how much his writing has improved. This is with the FES orthosis. He's not able to even pick up a pen on his own. Thank you. So this is the video of him doing the task. You see a huge improvement from day 1. I think this was somewhere in the middle. And then towards the end, where we started the checkers, you see how much his fine motor skills has improved. He was paralyzed in 2016, so about 5-6 years. Actually, 5 years up to the time of the study.
Story that
A little bit of spasticity, but with the FES, yeah. I mean, with the FES, that electrical stimulation over time, I think that like muscle tone improved, the strength improved, and so it has also a rehab effect receiving this consistent stimulation.
Not only the muscle, but also the actual hand cortex. So the hand cortex hasn't been used, and that was one of our controversies. Is do you put the electrodes over the foot, where we know, that, or the, somewhere over the shoulder, where we know he's been using the shoulder, or you put it over an area where we think is going to match the function, but yet hasn't been activated in so many years.
So back in 2016, 1 year after the injury, he came and did the EEG study. He did not qualify for the invasive surgery, given he was under 22. There was improvement, but we did not see such consistent improvement. And I think our whole team would agree with this, that the success of our study, majority of it is dependent on our subject. He is super motivated. He keeps us on our toes. And now that we've finished the trial, he's actually given us quite some engineering challenges to take this to the next phase. One of which, this did not come from him, which actually came from Dr. Cahigas, in the brain-machine interface. We really wanted to see if this whole part of using any device is actually possible. Like, can we have him walk with this signal? We implanted above the hand and arm knob. Can we use the same signal to have him walk? And can we do a brain-machine interface closed-loop trial with him walking? Would the signal be reliable? Is there going to be noise? And this had not been done. So after the first 10 weeks of upper extremity tasks, we started the lower extremity tasks. So our system looked pretty much exactly the same, except instead of the FES, orthosis for the hand, we had him put in an ambulator to walk. Experiment was exactly the same, where he was displayed instructions to relax and move his right arm, and then we had him in the in the ambulator walking. A lot of things led up to that. We realized that he hadn't stood upright in years, so a lot of work went in between here and when he was actually able to stand upright.
I'm sorry, you haven't moved the electrodes?
No.
It's still in the same place?
It's still in the same place. He's thinking about moving his hand. So this is very unusual because he's thinking about moving his hand and we're asking him to walk. And this is one of the questions we had, is this possible? Is this going to work? And it turns out yes. Can we have sound in this one?
The idea is you have this very robust binary signal you can create. It's like a yes, no. So could you use it in a sort of task-specific manner so that you say, now you're going to be walking, can you control it by starting to walk? So it's under his control, but you give him the task. So he's able to control that timing essentially when the task would start and stop. He's modulate whether the task is done and when it stops.
And why this is important is this gives us proof of concept that, yes, we can use, like I said, any modality for him to be able to control. So if he wants to control a hand, which is actually what he wanted to do, so we moved back to the hand after week 29, he actually wanted to be able to open the door to his house. That's what we're working on now. It needs to be something practical that this person can take home. Right now it's confined to the lab, but again, having him on the ambulator give us proof of concept. Yes, if he wanted to do any other modality, if he wanted to have his bed raised up, we could do that. Anything is possible. And that's why this result is so exciting. So again,
I'm sorry, excuse me, but could I just ask, I'm still trying to put my mind around the ability over the hand region to actually activate walking. Is that because of the plasticity of the cerebral cortex after spinal cord injury? Therefore you have more communication with different...
he is actually not thinking about walking. So early in the trials for the walking, he actually would think about moving. We got very low accuracies because we targeted the surgery and we placed the electrodes above the hand and arm knob, so we should not be getting any walking or leg movement in it. So when we asked him to think about moving his hand, then we saw pretty good accuracies, actually even up to 100% accuracies in some of the sessions. Unlike the hand orthosis, this was the range was higher in the accuracies. Some days he was actually more tired. We had to bring him down from the ambulator. His blood pressure would go down. But overall, he was still able to maintain a pretty good accuracies. Does that...
The results are quite variable there for a number of reasons, including the fact that, he hasn't been upright in years and gets fatigued. That's one big one. The other one is concentration. So he needs to be thinking about moving the hand every time he wants to move his legs. And there's a lot of noise. I don't know if you guys have been in the lab in the gym downstairs. There's other people down there, and so sometimes people are chatting and it's sort of a concentration thing. But overall, it shows that if he is focused and thinking about moving the hand every time he gets this command, then the results of our decoding were very stable over time.
Dalton, if your question is about plasticity, I've seen across the cohort of subjects that have done work like this, you can remap their cortex onto pretty much anything. So control multiple robotic arms or control a virtual kind of environment. So I think there is a possibility of that too.
And as far as his own body, you definitely have the tools downstairs to counteract his lack of movement by using electrical stim bites and others to get him aerobically beefed up, and metabolically you can deal with his postural hypotension with simple medications that are available, non-toxic. So there's a combination holistically of what you can do to empower him to operate better even.
And that... Thank you, and that's exactly the point, what we want to put forth. Brain-machine interface is actually one of the viable options for this patient population to be considered. Not the one and in all, but in conjunction with several other therapies can prove to be very useful. Another thing that, like Ian said, the reason for the fluctuation in accuracies, he actually started falling asleep on the walker. Which was not expected. We would expect him to fall asleep when he's just sitting his hand open close. But turns out because this one is, each trial is very slow, it takes, and we couldn't increase the speed of the walking due to safety concerns. It was very boring for him. At first it was very exciting, but he's like, okay, I need to be able to walk faster. Well, like, we cannot do that for safety, for your own safety. So he would fall asleep, and we would have to start the session all over again. So, yes, definitely, yeah.
Yeah, I mean, though I think it correlates more with the fact that this subject is, his vision of what is going to happen with this technology is so far ahead that it's very exciting for him to see it initially. He's like, okay, now I'm walking, so what are we going to do next? And so as an engineer, on the engineering side, it's a big challenge because you spend weeks perfecting this walking stuff. It was 2 years to get sort of this company that's got an FDA-approved device to make modifications to do this walking, and then he does it for 2 weeks, and now he's falling asleep. So you're like, all right, so how are we going to take this to the next level to keep him engaged?
I think that's one of the advantages of being here at the Miami Project. We do have a subject population that is this motivated. And I think that's very unique for us here. We have had people flying in from overseas to do the EEG study to see if they qualify for the clinical trial. So we really have an advantage here at the Miami Project, and it's great to be here, honestly. Any other thoughts or comments before I move on? So in conclusion, we wanted to make sure that, again, since this patient population has not used their hands or legs in quite a while, minimum 1 year post-injury, we wanted to make sure that the event-related desynchronizations were able to interpret those, that they were still able to generate a motor command. And I think from the results, we all agree that we have done that. And another thing, again, very early on, I showed you some of the clinical trials that happen in this area. You have 96 channels, 64 channels. We're just using 2 raw channels and 2 power channels, which was engineering. From the engineering point of view, one of the questions we had was, is this even possible? Like, how many signals can we expect to get from just 2 when in the field, in other studies, people use 64 and 96 channels, or sometimes 2 arrays of 96. Can we do this with just 4 channels? And again, it's not a highly sophisticated signal, but even with that simple signal, we're able to do so much. And we've seen that with the Jepson-Taylor hand function test, his performance has been phenomenal. Again, like I said, he was not even able to pick up a pen with the FES in week 1, and by week 29, he's able to write with little difficulty, but he's able to write something that we can read legibly. So, yes, and I want to thank and show you full team, some of whom are already here. I want to thank our funding people. Medtronic donated the device, and Miami Project and Neurosurgery and UM has helped us a lot. And yep, any questions or comments? Thank you.
I would like to ask, since we have such horsepower in the audience, what are the possibilities of doing this non-invasively in the future? You know, we know now that we can penetrate the scalp and skull with magnetic stimulation. 20 years ago, started in the basement of the rehab center. Now it's used in every operating room in the world, the magnetic stim. 30 years ago, I guess. But the question is, do you foresee that this could be done in your original array type configuration with a cap on the head, so that you could recruit other parts of the cortex, and if you can bridge that gap, electronically or electromagnetically?
You want me to answer that?
I was looking because you're so good looking.
I can also give you an answer, but if you'd like to go first. No? So one of the programs that I launched right before I left DARPA was to do exactly what you say. Can you take an injectable kind of an interface, but that uses either magnetic or acoustic signals in order to less invasively get the signals out? I think over the span of the next 4 or 5 years, we're going to see those technologies proven out, and you may not have to have a craniotomy in order to put in the sensors that you would need. So I think that there is a possibility moving out into the future to do exactly what you're saying.
So these guys should learn how to wash cars and do other stuff.
And you don't need the surgery. We're out of business. So we just submitted a grant on these electromagnetic nanoparticles that you can actually be used systemically, and then through completely non-invasive approaches, you hopefully can stimulate particular areas of the brain. Brian Noga and those colleagues are actually looking at the brain stem for these descending tracts that activate motor systems. So that's one component of what you're talking about. But what my question is, in terms of the current technology, I understand that we're pretty dependent on this Medtronic's software, hardware. Hardware. So is that something that's limiting in terms of doing this in more individuals as we move forward, or what is the next limitation or step that we have to think about in the next year or 2 years to kind of move this program forward?
There are, sorry. Medtronic PC plus S is one of the solutions, but that's by far means not the only solution. There are other devices. Actually, a group in France has already reached out to me. They have a 64-channel array so we do have options, but we do need the funding to carry the study forward. This is our first subject. You want to add to that?
I think the group in France was driven by Noeline Prins and a team of engineers, and they did a very sophisticated study that was published in the Lancet in early October, where they did bilateral implants, and they have many more channels. They were able to have a subject control, quadriplegic subject control an exoskeleton that's actually ambulating over ground, not on a treadmill, and also control up to 8 different degrees of freedom of the upper extremity. So they're able to do, but they use the same paradigm of these event-related desynchronization. So it shows that sort of this paradigm is robust and you can use it for more sophisticated control. I think what Noe's saying, there are some options. This would be the other option. They're looking to come to the U.S. And get an IDE type approval through the FDA. The main limitation is that currently in the U.S. market, there is no device like the Medtronic PC plus S. They had an in-between model that was the rechargeable, but then again, that's been phased out for research. But their new commercial device that's coming out in about maybe 12 to 16 months does have sensing capabilities, and then that will be sort of, we could use it off-label in that sense. It'll be an FDA-approved device that has sensing. So there is going to be something there. The ability to extract those signals and use it is probably going to take longer than their market launch, because they're not aiming to release that when it comes to the market, but it'll have the capability. So at least in the year and a half, there should be something that we could be implanting. Currently, though, our hands are pretty tied, because it requires getting an FDA ID for this company in France, which is going to be a long process, or convincing Medtronic to provide us with the RC plus S versions that are still out there and available.
So, is someone from Medtronic's here in the audience?
No.
I'm just curious, because I know Boston Scientific is excited about getting into this area too.
They're in this area,
Yeah. So
but they're not excited about doing what we need.
Well,
They're doing electrodes, right?
no, but there's an interest in this environment, a strong new interest by them. So I think they're interested now more than they were before. But the idea is that I think we need to make people interested and make them realize the market size and the potential. And I agree, we're a generation away from making this practical for the millions of people. But a generation can move quickly if there's an impetus. So.
Yeah, and the other thing, and speaking of devices, so the other thing is there are limitations about getting more patients because of the device market. But you can think about, can you do more things with the patient that we currently have? And I think this is what's very exciting right now. And one of the reasons that Justin is here today is that we're going to be interfacing this device with some of the stuff that is available at the TEL, and giving our subject more options to use this device with other gloves, with other potential interfaces, and we're working to move it so that he can have something to use at home. So during this time, we won't sit idle and wait for a new device. We'll try to get a pipeline of everything that can be done with this very rudimentary setup of just 4 contacts and 4 channels to extract data, but take it to the max and make it so that we can have patients get this and use it in a home environment.
So Mark, building upon both of these comments, keep this subject going in the best way possible. Try to get into the home environment to show the functional effects of doing that. At the same time, lean upon Medtronic, Boston Scientific to take their closed-loop devices and turn them into commercializable products that we could tap into. And then try, once that happens, expand the patient population that actually can receive these technologies.
Can you tell us so that we understand what Patel is and
Sure.
how this concept evolves? Because the world is changing rapidly.
Yeah.
And I was just out in California where a lot of this is emerging out of the soil.
Yeah. So just to put a whole context around it. So when I left Miami to go to work for the government, it was right when the BRAIN initiative was happening. And the big push on the BRAIN initiative was to invest a few $1 billion of the government's money to build the field of neurotechnology. And what came out of all of that was multiple centers sprung up across the country, Battelle being one of them, where people living with paralysis started using a direct brain interface with control of either robotics or muscle and things like that. Battelle has one subject that has been implanted, high cervical spinal cord injury, but just like Noe was showing, Utah Ray to a sleeve that goes on the forearm and can do very dexterous kinds of movements. What Battelle really brought to the table on all of that is you have a commercial entity that can take early stage science and turn it into a real product that could actually be put out into the market. So what I see this new partnership as being, you've done some of the foundational work. I can put the horsepower of Battelle behind it. We do device development, early kind of clinical trials, and then maybe even spin that out into a new set of products and help the entire field move forward. It's really bridging the academic to commercial kind of enterprise.
Which makes sense because the academic is so constipated bureaucratically.
Yeah.
The government is so constipated bureaucratically. So if you could bring the energy and flexibility of entrepreneurship, working with those two frozen entities, I think there's a great potential to achieve.
It's precisely the reason why we're trying to bring all of this together in this way.
Yesterday
Count
we
us
heard,
in.
so yesterday we heard about a new kinase inhibitor that's been discovered by Mind Project scientists that make the corpus spinal tract regenerate more than anything else that's ever been published. So we'll be talking about that in terms of moving it to the next level. Merging that with what the technology you talked about. Can you imagine electrical
Wow.
stimulation, brain-computer interface with regenerating the central nervous system, plus the ability to put stem cells and Schwann cells into people now genetically manipulating cells. So, and then the boot camp, the exercise, rehabilitation to affect the systemic effects in terms of skeletal muscle systems, cardiovascular. So we've got the whole thing that we're thinking about here. So it looks like to me we're at a really good time in terms of merging the academic approach that we're using, the biological approaches with the engineering. So it's a good time for us. So we just have to kind of come up with a vision. There's a new program that Dr. Green is initiating, the Nick Bonacani new award. It's a bench to bedside, and these are the types of programs we'd like to put money in to actually be able to advance. We know there's a lot of excellent research being done globally. I think we have an opportunity to contribute to that in the ways we just talked about. So it's pretty exciting.
Yeah, yes, I agree. Thank you. I do want to leave you with one last thing since we've been talking about next step. Like Ian said, we're not sitting idly by just because the clinical trial ended. Our patient would not want us to do that. He did a very invasive surgery, and he wants to use it. He wants to go home and open his door with this. So we had some challenges with the Bioness device, and that's why Sanchez is here with Battelle to take on to the next step. But as an intermediate step, we got a mechanical glove. The company gave us the left hand, and we were like, can we do this? Like, he hasn't used his left or right hand in years. He's not left-handed. So we put it on his left hand. We asked him to think about moving his right hand and still do the trial. And these are the results. our subject as well. Like, again, like, we would not be able to do any of this. Some of the other trials, the subjects would come in, will be moody and say, look, I don't want to do this today. I don't want you to be testing on me. But he's here 3 times a week, several hours a day, saying, like, I'm going to do this, and I want you to make me do it. And I'm going to make sure that you actually get the technology working to do that. We also had him play some games.
And this was an orthosis that he found.
Yes.
This is,
Yes.
the subject went
Yeah.
online, found this device, and went to you guys and said, I want this device.
Yeah.
This is what I need.
And
Let's take some of his blood and inject it around the room.
I mean, he's.
that's exactly what we need.
I was doing the adverse events for the week, sitting down and just saying, hey, how are you feeling? How'd the week go? Et cetera. And he's like, have you heard about this glove that this company in San Francisco is doing? They have a GoFundMe page or something like that. And I literally, like, after I did the adverse event paperwork, I gave it to Letitia, I shot them an email. I said, hey, with the University of Miami, we're doing this. Our subject that just got a brain machine interface wants to try your glove. And there it is. They sent it to us. No questions asked, so that we can integrate that equipment.
And we had a very generous donor give us the money to actually get 2 gloves so that he can take this home someday. We also, early on, I showed some of the other trials that do computer stuff, and we had him play this game. Again, this was completely brain controlled.
So move the cursor up, and relax, move the cursor down. And he thinks about moving his hand to bring the paddle up on the screen. This is also potentially a good way to start people training, say if they're in the hospital and we're going to do this in an early phase and we want to look at what their brain signals are doing, you could bring a game like this, record either an EEG or the early data, and use it to build the decoders.
This was actually a stepping stone for us to eliminate this trial-based system altogether and just have him, no instructions displayed on the screen whatsoever, just have him move his hand on his own volition. So there's nothing displayed on the screen. If you notice, it takes a while for him to open his hand, but the closing part happens pretty well.
This is the hand without the electrodes.
Yes.
Yeah, so he's thinking about moving his right hand, keeping everything steady on the right hand, and then using the left hand to control.
I'm sure Jonathan will get
And this though, the key here though is that, we should express is that there's no visual cue to do this anymore. He's doing this just on his own, right? So every other paradigm we've seen so far is, he's gotta have a visual cue to activate wheels. Now, they're trying to get it so that, and that's one step closer to being outside the lab, right?
Exactly.
Be able to do this in a home setting. So, I mean, I think we have huge advantages here, right? We have some mild disadvantages, which is the resolution of the signal, but I think we have some major advances in the fact that this is, again, fully implanted. This will be the first device to be used in a home if we can continue to move this forward. Those devices where you can do a lot of different things are great in the lab, but you're not gonna be doing that in a home setting. And I think that's what we need to capitalize on. We need to show that this is useful to somebody in their home.
I sent this video to my former advisor at MIT, and they were so excited that we now have 4 people at MIT working with us to develop the algorithms to make this more accurate, to extract better features. So now there's like 2 postdocs and 2 PhD students that I talk to regularly about getting this technology moving forward. So it's like super exciting where it's placed us sort of on the academic sphere.
Yeah. And it's a huge advantage, like I said, to be here at the Miami Project, where paralysis is tackled from different ends, and we're seeing strides in all of it. And it's great to work with such a great team. Thank you.
Congratulations, Pete.